Okay, well, we'll get started and see if anyone else shows up. My name is Katie. I'm actually one of Dr. Green's grad students, and she asked me to cover for her today. Before we jump into the PowerPoint and examples that she sent me, do either of you guys have any questions? All right, let's see if I can get this. Jump into my screen here. Okay, so just to get us started, there's a couple of questions about sort of the theories. So here's our first one. Either of you want to volunteer to answer? I know it's a lot of pressure since there's only two of you.
Is it D?
D or D? I couldn't quite make it up.
D.
It's actually the law of definite proportions. So multiple proportions is slightly different. Multiple proportions is when so you can have different things with you can build different molecules out of the same elements, whereas law of definite proportions means that if you have, for example, water, if you have water, regardless of where you find it, water on the moon, water on Earth, water on an asteroid, wherever you find it, it's going to have the same proportion of hydrogens and water and oxygens.
So just no matter where you're at, it's all the same for a definite proportion. Okay.
So you're going to have water that's going to have two hydrogens and an oxygen no matter where you find it. Are there any questions?
Ms. Smith?
Mm-hmm.
I'm so sorry, but I haven't watched the videos yet. I thought I'd come in and see kind of what was going on in the Zoom session, but I think I'm a little bit lost. Will this be recorded that I could watch later?
Yes, I'm recording
Okay,
it.
I think I'm gonna go watch those because it's a lot earlier in California right now. I didn't get the chance to finish everything quite yet.
Okay.
Thank you so much, though.
Yeah, no problem.
Have a good one.
Okay, so the next question is,
B.
yeah, so this one is D.
Oh.
So this is what we were talking about just a second ago. The law of multiple proportions is, so here it shows carbon dioxide and carbon monoxide. Both are made out of just carbon and oxygen, but in different ratios. So they're two different molecules.
Okay.
So definite proportions means that if you have a carbon dioxide, regardless of where you find it in the whole universe, you will have one carbon and two oxygens.
Okay.
And then multiple proportions is that you can make both carbon dioxide or carbon monoxide out of specific ratios of carbon and oxygen.
Now, Were there videos leading up to this too? Because I've been here for all the Zoom sessions, but I don't remember going over this whatsoever. So is this supposed to be all new stuff?
I'm not sure. This is just the information that Dr. Green provided to me. I'm not sure how far y'all got or if there were videos on this before.
Okay.
So these are just basic laws that we tend to, we just use to sort of define how we can use the elements and manipulate them to build different things. The most important part is to know what they mean, not necessarily the official name, but like know that you're not going to put like multiple proportions and definite proportions. Basically mean that you're not going to build a molecule out of one carbon and half an oxygen. You're going to have a whole oxygen and a whole carbon. And wherever you find that carbon monoxide, it's going to have those building blocks in that ratio.
Okay.
So multiple proportions is the 1 carbon and 2 oxygens, 1 carbon, 1 oxygen. You can have any ratio, but they have to be whole numbers. So there's a couple of different things here. Which one do you think would be an example of the law of multiple proportions?
B.
Very good. Very well
And
done.
so it has to be a whole number, and it can be the just a whole of one element and the other element, and then carbon that could just be whatever amount.
Yeah, so these are just the carbon dioxide and carbon monoxide are just the example because they're fairly common. Like we know what a carbon dioxide and a carbon monoxide are, but it could be anything. It could be silver chloride. It could be anything. So that's why there are the generic different compound possibilities up here. So then this is a little bit more involved. So if we have 2 different options for sulfur and oxygen forming molecules, right? We can find, so say we have some sort of sample and we decompose it, and the sulfur dioxide would decompose into 3.49 grams of oxygen and 3.5 grams of sulfur, whereas sulfur trioxide produces 6.75 grams of oxygen and 4.5 grams of sulfur. We can find the ratio of those in order to prove or corroborate the law of multiple proportions. So if we take the masses, we can use them to calculate what our ratio is for the two.
Okay, so we find the masses of each one.
Yeah, so we're given the masses, so we need to get the ratio.
Okay.
So we just need to get a ratio of the two of them. So all we really need to do is divide, right?
Okay. And do we have to do sig figs in this?
Well, we're given 3 sig figs for each of them, right?
Right,
So we want to stick with 3 sig figs
okay,
because sig figs basically tell us how much we can trust our numbers. So with 3 significant figures, we can trust it to the 3rd significant figure, but after that, we can't really trust the number. It's not as
Okay.
exact.
So for 6.75 grams and 4.50 of grams of sulfur, I got 1.5
Mhm.
grams. And then I got 0.99 wait, I got 0.99 for the other one. Let me just double check that number. Round, so would it just be one gram?
So it's 0.997. It's about 1, but because we have those 3 sig figs, we can take it to that 3rd sig fig.
Okay, so that's when we just don't round since it's only 3 significant figures.
Yeah, because we have all 3 and we want to know it to the 3rd significant figure because we want to be as exact as possible.
Okay,
And because of 3 sig figs, we include that 0 because we know it's 0.50 and not 0.51 or 0.52.
okay. When you're in lectures, do you take notes during lectures or do you like skim through some of them and then just do the rest in your dorm or like outside of class?
Oh, for like example?
Yeah,
I mean, this is our last example before we jump into more lecture stuff.
yeah,
I was just going through the PowerPoint that Dr. Green gave to me, so this is the stuff that she wanted y'all to go over.
okay,
Yeah. So we have our 2 answers from the last slide. This is all just the last slide. When you combine 2 elements, you have to have a whole atom with a whole atom, right? So even though we have these decimals, that's because it's in grams, you can weigh out masses in decimals, but not actual elements. So you apply that law to get a ratio of small whole numbers,
when it's a compound.
and that gives you that there's 3, because we have 1.5 and 0.997, we can round those to 1.5 and 1, and we get a ratio of whole numbers when we multiply it by 2 to get the 1.5 to be a whole number.
Okay, so when
So that's how we get through 3.
when it's a compound, we can round to make it a whole number. Okay,
So since we can simplify all of this to a ratio of whole numbers, 3 to 2, they're not decimals anymore, that means that the law of multiple portions is upheld.
okay,
Basically, we didn't break science.
okay.
So just as a quick overview of the history of atomic theory, it took us a while to actually figure out what atoms were. And there were several now very famous experiments that were done. So Robert Boyle came up with the experimental definition of an element, which is basically an element is something that is composed of all of the same thing. It's the basic building block, and it's definitional. And then Dalton's atomic theory came up with these 4 basic principles. Each element is composed of tiny indestructible particles called atoms, basic building block. All atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements, which means an atom of oxygen is going to be like all other atoms of oxygen and is going to be different from all other elements. Atoms combine in simple whole number ratios to form compounds, just like we talked about. You can't put a half an atom with another atom. You have to do whole atoms. And then atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way they're bound to each other. So Dalton was saying that an atom is not going to change into a different kind of atom. In a chemical reaction, you're only going to change how they're combined. But we still didn't really know what atoms looked like, so or how their charges were arranged. So J.J. Thomson did the cathode ray experiment and discovered the electron. There was a negative piece and a positive piece. Robert Millikan did the oil drop experiment and found the mass of an electron. And Rutherford did the gold foil experiment, which led to our now nuclear understanding of an atom. So Rutherford disproved what was essentially
Splitting of the atom.
not splitting of the atom, but he
Lighting.
disproved the plum pudding model. Have you heard of the plum pudding model?
No.
Okay, so here's essentially moving from left to right, how we understood the atom over time. So John Dalton thought it was just basically a tennis ball. It's a tennis ball, it's solid, it's a marble, it's an atom, and they aren't indivisible. He was wrong in that we now know that there are negative and positive parts. So Thomson came up with the plum pudding model, which we don't, as Americans, we don't really know what plum pudding is. So I think let's just think of a chocolate chip cookie, that the dough is all this positive charge stuff, and then there are little pieces of negative stuck in it like chocolate chips. But then Millikan ran the oil drop experiment and found the mass of an electron and the charge of an electron, so he was able to put numbers to those. But then Rutherford ran the plum pudding, destroyed the plum pudding model idea by running the gold foil experiment, which was basically he took a really, really thin sheet of gold foil, like atom thick, and he shot alpha particles at them, and he measured where the alpha particles went. So when he was doing it, the alpha particles usually just went straight through the foil and hit the back of the detector. But sometimes they got knocked at really sharp angles, meaning they were hitting something solid and hard that wasn't letting them pass through. If the plum pudding model had been correct, it would have just blown a hole because it's a soft, gooey, positive stuff. But instead, it hit a nucleus, and most of the time it went through the empty space around it. And then sometimes it hit the nucleus and bounced back at super sharp angles. So Rutherford found that we have a nucleus and then it's surrounded by the electrons. And then Bohr came up with the idea of the electron sitting at very specific energy levels. And this is how we tend to think about it a lot of the time. We have these very specific energy levels, but the electrons don't move in these nice planetary rings. We now know, thanks to Schrodinger and other people, that electrons exist in sort of a cloud. And that's the way that we know that you can know where it is, kind of. So we draw these, like this sphere, but this really only encompasses like the 99% chance that the electron is somewhere in there. There's a chance it could be anywhere, which is very weird. Electrons are very weird. But Schrodinger showed that they don't follow those planetary rings. Instead, we have orbitals that are in different shapes.
And who's Millikan?
Millikan ran the oil drop experiment.
Okay.
So he ran the oil drop experiment and he found the charge of the electron and the mass of the electron.
Okay.
So our nuclear theory of the atom, now that we know that there's an electron around a nucleus and the nucleus has the protons and its positive charge has neutrons, now we can start to define elements by the pieces that make up their atoms. So we have protons and neutrons in the nucleus, and then we have electrons whizzing around outside. We know that the protons and electrons are much heavier than electrons because Millikan found the mass of an electron and the mass of an atom total is much bigger than that. So we tend to define, we always define these as atomic mass units, which is just the unit defined by carbon. So the mass is going to be the number of protons plus the number of neutrons, because the mass of the electrons is negligible. And then the atomic number is the number of protons. So on a periodic table, you'll be able to find an element with the chemical symbol, the full name, the atomic number, and often the mass. Ions are just elements that have extra protons or extra electrons. They gain and lose electrons. You cannot gain or lose a proton because those are in the nucleus. If you take away a proton, you have changed the element because we define the element by protons.
So a positive or negative ion will change a proton or electron.
So we're only changing the electrons. We can't change the protons. Because
Okay.
if you take a proton away, you have changed the atomic number. You've changed what element it is.
Okay.
So we define elements based on the number of protons, and we can change their charge by changing the number of electrons. So the only thing about an atom that's going to change is going to be the electrons. If you take away electrons, since electrons are negatively charged, if you take away electrons, you're going to end up with an overall positive charge.
Okay.
And if you add electrons, give an atom extra electrons, you've given it extra, so you're going to have a negative charge. An atom is neutral and not an ion when the number of electrons and the number of protons match.
Okay.
In general, when you're looking at a periodic table, the metals, which are in all the transition metals, but then the metals are on the left side of your periodic table.
The ions can change randomly, like on transition metals. It could be whatever.
So transition metals can have multiple ions. So you can have, like, iron can have a charge of 1, 2, 3, and that just depends on how many electrons you've taken away. But things on the far left side of the periodic table, like sodium or calcium, those are going to have a definite charge. A sodium
Like
is
1,
always
2.
going to be +1.
Okay, +1. Okay.
Yeah, so the atoms on the left side are going to be positively charged, and usually things on the right side of the periodic table are going to be negatively charged. So the anions like fluorine, chlorine, oxygen, those are going to be negatively charged.
Are negatively charged ions?
Mm-hmm. So the number of electrons and the number of protons are how we determine the charge. So fluorine has 9 protons because its atomic number is 9. It means that the nucleus has a +9 charge. So for fluorine to have a 1 negative charge, it has to have 10 electrons.
Or else it would just be equal, right?
So if it had 9 electrons, it would be equal.
Okay.
And then calcium has 20 protons, has an atomic number of 20, has a plus 20 charge in the nucleus. So a calcium with a charge of 2 plus is going to have 18 electrons, meaning that it is missing 2 electrons to be neutral. So it has a plus 2.
Okay.
On a periodic table, you'll find sort of this setup sometimes. You'll have the chemical symbol, which is like the F for fluorine or the Ca for calcium. And then the mass number, which is how much it weighs. So that's the protons plus the neutrons. And then the atomic number is the number of protons. And that's how we define the element. So all atoms of the same element have the same atomic number. So
Oh, that like are in the same section.
just an element. So like all oxygen, right?
Okay.
All oxygen has the same atomic number. What's the atomic number of oxygen? Do you have a periodic table?
I can look it up real quick. Which one did you say?
So oxygen, what's the atomic number of oxygen?
15.99.
That's the atomic mass. That's the mass number.
Oh,
So
8.
what's the 8? So that means oxygen has 8 protons,
Mm-hmm.
and that's how we define oxygen. So wherever you go in the universe, if you find an oxygen, you define it by having 8 protons. If you have an atom with 8 protons, it is oxygen.
And then to find number of neutrons, you take that and minus it from the atomic mass.
Mhm.
Okay.
The reason why the mass on your periodic table is not a whole number, the reason that it's a decimal is
Yeah.
because we have isotopes. Isotopes are what we call atoms that have a different number of neutrons.
Okay.
So the proton is always going to stay the same. If an electron number changes, it's an ion. And if the neutron number changes, it's an isotope.
Are you able to repeat isotopes again? What's an isotope?
It's a different number of neutrons. So for oxygen, usually it has 8 protons and has 8 neutrons. They add up to 16, everything is good. But sometimes there are only 7 neutrons. There are still 8 protons, so it's still oxygen, but there are only 7 neutrons. So it's a little bit lighter.
So if it's not equal to the number of protons,
Right.
then it's an isotope.
So the mass is different for that atom, but it's still oxygen because it still has 8 protons. The reason why the mass of oxygen is so close to 16 is because those isotopes are very rare.
Okay. Now I've seen on different periodic tables, the atomic number is a little bit different on each one. Why is that?
What do you mean the atomic number is a little different?
No, the mass number.
Oh, yeah. That's how many sig figs, if they rounded. Usually it's going to be pretty much the same. It should be the same. It probably, the difference is like the 3rd or 4th decimal place, and that's rounding or truncating.
Okay.
So just to give us some practice, let's try matching each of these to their description using the periodic table.
Okay, let me pull it up again.
Okay.
atomic number 23. Chromium has atomic number 23. Oh, vanadium. Vanadium.
There you go.
I was looking at the one next to it.
No worries.
Okay, contains 10 neutrons and 10 electrons is in its preferred ionic state.
Okay, so we need to talk about preferred ionic state.
Okay.
Let me just pull up. I want to pull this. Can you see this?
Yeah.
Okay, so like I was saying, so here are the transition metals. These can have multiple ionic states. Here on the left, we're going to have positives. We're going to have cations. And over here on the right, we're going to have negative charges or anions.
Right.
You can figure out what each of these want. Well, I say want. The preferred ionic state of each of these by counting in. So here it's going to be +1. These all want to be in +1, and these all want to be +2.
Okay.
Same over here. So we have our noble gases, which have a charge of 0.
Mm-hmm.
And then we have -1 and -2.
And that can mine it in the next row can be -3 or
It gets a little muddier here. These don't tend to have very common, they don't tend to form ions as often. You're not really going to see a carbon ion floating around, but
okay.
you will see a fluorine ion. Like salt, table salt is sodium chloride. It's 1 sodium and 1 chlorine bound together. When you dissolve that in water, you don't have sodium chloride around. You have a sodium ion, so an Na+, and a chlorine ion, Cl- floating around.
Okay.
You're not going to have, if you put, like, when you dissolve sugar, you don't have individual carbons. You have a whole sugar molecule.
Okay.
And that is ionic stuff for later. For now, +1, +2, 0, -1, -2. And that's the information that you're going to end up needing to work this. So it contains 10 neutrons and 10 electrons in its preferred ionic state.
Okay. Neutrons. State. Okay, I'm a little confused on how to figure this one out.
Okay. So first, it's going to have 10 neutrons, which means that it's going to be, the mass is going to be bigger than 10, right? It's going to be at
Okay.
least 10 because we need to have protons. With 10 electrons, we're going to have about 10 protons, right? It's going to be somewhere between 8 and 12 protons, right?
Mm-hmm.
So we can start with oxygen, which is 8. If it has 8 protons, if we gave it 10 electrons, what would the charge be?
18.
So if we gave it, so it has 8 protons, right?
8 protons, okay.
8 protons are positive. If we
Mhm.
gave it 10 electrons,
Oh, okay, -2.
-2. That sounds reasonable for oxygen. But if we look at the mass,
15.
so with 8, so if we have 8 protons
Mhm.
plus 10 neutrons, right? That's going to
Right.
give us a mass of 18. What's the mass of oxygen?
16, basically.
16. So we're 2 neutrons heavy.
Oh, so it's fluor. I don't know how to pronounce that. The
So
one
if we
that,
so fluorine,
yeah, fluorine.
if we try fluorine, let's try fluorine. So if we now have 9 protons, right? Because that's what we define a fluorine
Mhm.
as, the atomic number of 9. If we gave it 10 neutrons, or we gave it 10
-1.
electrons, take this -1, that works. That's what fluorine should be, right? Because
Yeah,
it's in that column. So then if we have 10 neutrons plus the 9 protons that we define it with, what's its mass?
19.
And the mass of the fluorine here is 19.
Yep.
There you go.
Okay. How would I write this down in the most simple terms?
So when I was a Gen Chem student, I had one periodic table. I just had a periodic table printed out that I just wrote everything on.
We can keep it with us.
I know that when you're taking a quiz or a test or something, you need to have a periodic table. I don't know if it's specifically a clean one or they'll provide you one. It was just mine for studying and doing homework and stuff like that. Was I just took my periodic table and I wrote +1 above this column and I wrote +2 above this column and I wrote the charges and I took like a helium and blew it up and wrote down what the 2 and what the 4 and what the symbol meant.
Oh, okay, like
And
atomic mass and stuff like that. Okay.
yeah, and I wrote everything on one periodic table so that I could use the same one to study off of.
Do they give you the names of them on the periodic tables that they hand you?
I think so.
Okay.
A lot of the time, the symbol is a pretty good hint as to what it is. So like sulfur is the S, right?
Okay.
Is 16. Phosphorus is 15, the P. Stuff like sodium is a little harder because it's Na.
Yeah.
And there will come a time, if you stay in chemistry long enough, that you'll have like the first 2-3 rows memorized. Like I can look at this and I'm like, yeah, that's gallium, that's bromine, because I've been doing this for 10 years.
Okay.
But it is probably a good idea if you're the flashcard type to do sort of flashcards of like up through probably like chlorine up to like 17 or so, and get and sort of like kind of know what the first 2 and the last 3 rows are.
Okay.
Many periodic tables give you the names. I don't specifically remember if the common one that they give you for quizzes has the names. Actually, I'll ask Dr. Conrad real quick. Give me 1 second.
Okay. Okay.
Shoot. She's not in her office. I don't think I have for the test or anything.
Well,
Yeah, I'm not sure.
okay, so this problem that we just did, it I'm still a little confused on it.
Okay. Do you want to do another one?
Sure.
Okay, so if we say we're like, okay, we're gonna guess that it's sodium. If we have sodium, Na, it has an atomic number of 11, right?
Let me bring up sodium. Na. Okay, I can't find it.
It's the very first column, third row.
Oh, there it is. Okay. 11
It has an atomic number of 11. What does that mean?
protons.
We have 11 protons. It also means that if we were neutral, we would have 11 electrons.
Hmm.
So 11 electrons. But what is the preferred ionic state of sodium?
1 plus 1.
Plus 1, very good. So in order to make it plus 1, what would we do to the electrons?
-1. Well,
We take-
yeah, -1. So it would add 1 to a proton. Oh, take 1 away from electron.
Take away from an electron, very good. Because we can't change protons. If we take a proton away or add a proton, so if we take sodium and we add a proton, we now have a magnesium. And we can't do that. So we change the charge by changing the electrons.
Okay.
So we have a sodium with 11 protons, and it would neutral, it would have 11 electrons, but we want a +1 charge because it's in the first column.
It's in the +1. So then it'll make it 23.
So 23 is the atomic mass.
Oh, that's atomic mass. Okay.
So the atomic number tells you how many protons, the atomic mass tells you how heavy it is.
Okay, so we would add a +1 to the electron state, which would make it 12. Okay, so then it'd be Mg.
Electrons are negatively charged.
-12, I mean.
So if we add an electron, we make it a -1. What does sodium want to be?
Sodium wants to be magnesium.
So
I'm so confused now.
you're okay. You're okay. Let's go from the top. Okay, so we have a sodium, right? We're just imagine we're holding a sodium atom. We can count 11 protons in the center, in the nucleus. 11 protons defines a sodium. No
Okay.
matter where we go in the universe, if we grab an atom with 11 protons, it is a sodium.
Okay.
In the sodium we're holding, we have 11 protons. Sodium would have 11 electrons to make it neutral,
Right.
because +1 and -1, they cancel out.
Mhm.
Sodium is in the first column of the periodic table,
Mhm.
which means that it wants a +1 charge.
Right.
In
So
order to make our
10.
neutral sodium +1, we have to take away 1 electron so that there's an imbalance. We have
Okay.
1 more proton than we have electrons,
Right.
which means that we're going to have 10 electrons.
Mhm.
So that actually matches our question here, right? 10 electrons in the preferred ionic state. Great. Now we need to figure out the mass. The mass of sodium is 23,
Mhm.
23 AMU. If we subtract our 11 protons, how many neutrons does that leave us with?
So we can disregard electrons at this point when we're doing this.
Right. So for charge, protons and neutrons, or protons and electrons. For mass, it's protons and neutrons, because electrons are so tiny and so light that we call their mass negligible.
Okay. So you said
So the atomic mass of sodium is 23.
23 and then 23 minus 11.
Because
Okay.
we have 11 protons, so the rest have to be neutrons.
So then we would have carbon.
So that gives us with 12 neutrons.
Oh, I'm still thinking of the atomic. Okay, I'm thinking of the atomic mass.
Yeah, so we now have, so the total atomic mass is 23
23 and then minus 11.
minus
12.
11, because we know that 11 of those AMUs are protons. So we
Mhm.
need to know what the rest of them are. So it's 12 neutrons.
12 neutrons. Okay.
Can I draw on this? I can. Ha, perfect. So in our little nucleus, we're going to have our protons, right? And we have 11 of those. The nucleus is made up of protons and neutrons all stacked together. So imagine kind of like if you had a bunch of marbles all glued together.
Mhm.
There's your protons and your neutrons.
Yeah.
We know that the total mass needs to be 23 for sodium. And we know that the protons all add up to be 11. Because we know that it's sodium and it has 11 protons.
Mhm.
So to get the rest of them, to get to 23, we need to have 12 neutrons.
Okay.
And that's the rest of it. Does that make sense?
Yeah.
Okay. Do you want to do another one just to practice, or do you want to move on to the next question?
Yeah. Let's just do one more.
Okay. So let's grab something fun. Let's do calcium.
Okay. It has 20 protons.
20 protons. Very good.
And then it has 20 neutrons.
How do you know?
40 minus 20.
Very good.
And then from that it has 20 electrons.
It has 20 electrons to be neutral, but what's the preferred ionic state?
Plus 2.
Plus
So
2.
it has 18.
18 electrons. Very good. Nice job.
Thank you. Let me write. Okay, I'm gonna write this down real quick, just like like that whole practice thing, so I can
Go
just
for it.
remember it. Okay, so after this, are we able to do one more just so I can have it stuck?
Absolutely.
Okay. Let's do a more difficult one.
Okay.
Well, I don't know if they're that much difficult, except for transition metals, but I don't know.
Well, transition metals become tricky because they have multiple ionic states. They can be
Okay.
different charges.
How do we know when it's in the 4A row? I think that's what it is. How do we know when it's a +4 or -4 ion?
Oh, so like carbon, silicon, those?
Yeah.
So the +1, +2 really only applies to the outside ones.
Okay,
Boron tends to play by its own rules in a lot of ways. Carbon is usually neutral. The kind of the six right there in the middle, boron, aluminum, carbon, silicon, nitrogen, and phosphorus, they don't follow the 1-2 rule. It's just the outside. So we have the +1, the +2, and then we have 0, -1, and -2.
okay. Okay, that makes more sense.
So what if we did, let's do iodine.
Okay. I'm gonna write it down.
Okay.
$53 protons,
Mm-hmm.
and then 73 neutrons.
I got 74.
Oh, wait, I forgot to do the. Yeah, I forgot to do decimal 74. And then electrons, wait, let me see what row this is in. Okay, so 3 to -2, 55 electrons.
Iodine is a -1 because remember the noble gases have a charge of 0.
Oh, -1.
So
Okay.
it's -1.
No, why? Okay, see, now I'm just making up numbers in my head. It has 52 electrons.
So if it has 52 electrons and 53 protons, what's the charge?
And it has a -1.
It wants a -1. How do we give it a -1?
We had a positive, so it's 50 as 54 electrons, but I thought you can't have more electrons than protons.
Oh, you can. That's how you get negative charges.
Oh, it's just protons. A proton is just always more than an electron in its mass or
And
whatever.
it's mass.
Okay.
So protons and neutrons are equal in mass. Protons and electrons are equal in charge.
Equal in charge, okay.
So if we have 53 protons, we need 54 electrons to make it a -1.
Okay. That makes more sense.
Okay, so if we real quick try this, this fourth one, it contains 30 neutrons in the nucleus.
Okay. 30 neutrons in the nucleus. 30 neutrons. How are you able to skim through elements so fast? Like, because you have to do minusing, right? Is that just what it takes? You have to just skim through it really quickly?
I just have 10 years of experience. You're all good. 30 neutrons on the nucleus. Okay. What are our options here? Selenium.
Oh, maybe let's see this.
No. Nope. Come on.
It's, I think it's nickel or cobalt.
That's where I ended up too.
Yeah, cobalt.
Oddly, that's not an option here.
That's not an option?
Yeah, sulfur, phosphorus, like I'm not seeing it here. So now I'm doubting myself.
So then it's a. What,
But I
what,
got cobalt and nickel. They have, based on how you round it, how you round the mass, they're going to have 30 neutrons. You're correct.
okay. So if it
Um,
came across this on a test, what would I do? Or would this not come across on a test?
I mean, a question like this might, let's try just eliminating answers, right? Okay, so sulfur. What is the mass of sulfur?
32.
Could that possibly have 30 neutrons?
But it can't.
It can't. So it's not going to be sulfur. So we can eliminate sulfur. What if we try
Okay.
phosphorus?
I'm guessing that one would be pH, right? We would look for pH.
Phosphorus is just P.
Just P. It can't be that because it'd be 15.
Mhm.
Uh,
Fluorine,
no. We already answered that.
manganese.
Uh,
Manganese is Mn.
it. Oh, I just lost. There we go. I'm guessing it's that one. It's 20. It came out to 29 for me.
We could round it up to 55. Minus the 25 takes us to 30 neutrons.
Okay, so
So manganese.
manganese. And do the exact same thing how it wants us, what I just did before on the previous problems.
Mhm.
Okay. And it has 25 protons,
Mhm.
54. Let's just say it has 30 neutrons.
Right.
And then this is
And that's how
transition
we-
metal.
Right. So manganese is a transition metal, has different ionic states. But this question is just which one matches. And so manganese has 30 neutrons. So here we go. It's manganese.
So in a test, would it tell us if it wanted us to figure out transition metal? How many
It would give you
electrons it had? It would give us.
it would give you a charge.
Okay.
Metals are usually given with the charge in Roman numerals in parentheses.
Okay.
And it's just a manganese with a 2 like this in Roman numerals. That would just be manganese with a +2.
Okay. Why is it in Roman numeral? Is that just because easier?
It's a convention.
Okay.
Well, it's noon, so our time is up. Do you have any final questions? before I let you go?
Do you know where to go on like a website or something to get more practice like this?
So the rest of these are good practice. I'm not entirely sure. I don't have access to Dr. Green's D2L, but she might have more practice up on the website on D2L.
Okay. Okay, so if I just come across a problem that says contains 30 neutrons, I just take the protons and minus it from the atomic mass to find which element. Okay, let me just write that down real quick.
Okay.
to that- and okay, I got it.
All right.
Thank you. I really appreciate it.
Yeah, no worries. My
You have a
pleasure.
great- Thank you. You have a great rest of your day.
You too.
Bye.